Hey folks, Mr. Jordan here, and this calculus lesson is on exponential growth functions and decay functions, so applications with this and compound interest. Okay, let's go ahead and get started with this. Let's build this first, okay? The first part was a lead up to these story problems. So part one of section 5.6 was a lead up to these, you guys. So let's go ahead and build our exponential one. So examine the rate of change of y with respect to t when proportional to y. Okay, so this rate of change of y with respect to t, that's this stuff right here. That blue stuff right here is this blue stuff, and proportion to y is this red stuff right here. Okay, so what I'm going to do is put the y's on the left and put everything else on the right, so I get to that stage right there. You guys with me? Then I'm going to integrate both sides, okay? And then the integral of this side is the natural log of y plus c. Integral of this side with respect to t is going to be kt plus c, okay? And so the both plus c's gets absorbed into 1 plus c because they're just numbers, you guys. So when you add and subtract numbers, you just get a number. So it's plus c right there. All right, let's flash back to algebra 2, you guys. Remember, this is base e right there. And if I was in base e, I'd say this base right here to this power on the right is going to equal this right here. You guys with me? So I'm going to say e to the kt plus c power equals that y right there. Now let's go back into algebra 1, you guys. And you remember this right here, x squared times x cubed. It's x to the fifth because I add those exponents. So when I see the sum of exponents, I can write it like this, is the base to the one power times the base to the other power. So this is e to this power times e to this power, and that's what this says right here. Okay, so and then what I'm going to do right here, this is just another constant right here. E to the c power is just a number, so it's just a constant. So I'm going to just represent it as this c right here. All right, so that's our formula. This formula is the formula that we use for many of our exponential growth and decay problems and compound interest problems. Okay, so here, y is always your final amount, c is always your initial amount right here. K is your rate of growth or decay or the percentage from your bank if it's an interest rate right there. Okay, and then just notice if K is if it's a decay thing, then K is going to be a negative right there. All right, and time is typically in years, so that's T right there. Okay, so most of the time you'll be giving 3 of these and you solve for the fourth one, but if you're only given 2, then a lot of times you're going to use the fact that it's a half-life and then solve. So for example, if the half-life is 20 years, and say you begin with 12, then it's going to be half of 12, which is 6 after the 20 years right there. Okay, and notice 12 and 6 have a ratio of 12 to 6, it reduces to 2 to 1. So it's a lot easier to use the ratio 2 to 1 on this stuff when you have half-lives right there. All right, so here's a radioactive decay in terms of half-life. Now, it's different numbers in different books, you guys, just a little bit different. So I found a resource online. Look what I found online here. These numbers, for example, this is 4,470,000. And then here in my textbook we have 4,510,000. So the numbers just vary a little bit from one book to another book. I don't know why. Probably because I tell my kids, I teach high school, and I say it's because they hate teenagers and they want to punish you guys. I don't know why they change numbers like this. Maybe it just changes after a little bit. I don't know. Anyways, but since my textbook uses these numbers, I'm going to go ahead and be consistent with my textbook and use these numbers right here. So this is the half-life, how many years it takes, or how many seconds, or how many days it takes for the half-life right there. Okay, so let's use that. So suppose that 10 grams of plutonium isotope was released into the Chernobylium nuclear accident. So how long will it take for 10 grams to decay to 1 gram? Okay, so the plutonium, we're going to use this number, 24,360 years for the half-life right there. All right, so here's my formula, y equals ce to the kt power. Remember, y is the final amount, c is your initial amount, k is your rate of growth or decay, and t is your time in years. Well, that's what I'm looking for, is my time in years. And I really don't know what k is, not yet anyways, but I'm going to use my half-life formula right here. Okay, I do know that my starting amount is 10 and my ending amount is 1 right there, so let's go ahead and plug that information in. Half-life of petroleum is going to be 24,360. So what I'm going to do is solve for K. So remember, and I won't use the 10 yet. I'm going to use the half-life, which has a ratio of 2 to 1. Starts with 2 and it goes to 1 right there. Okay, and then of course it's e to the kt power, where my t is 24,360. Okay, so then I divided both sides by 2, so 1 divided by 2 is 0.5. So 0.5 equals e to this power right here. And then I'm going to natural log both sides. So the natural log of 0.5, you guys, I did that right here, equals, okay, the natural log of this is just the exponent, 24,360k. Then I'm going to divide both sides by 24,360k, and it gets me k to be negative 0.00002854. So this K right here now goes right here, okay? And then I can go ahead and plug it into this formula. I have everything to plug into the formula right there. Okay, so now I'm going to plug in my initial amount, my final amount, and then there's my K right there. Okay, I'm going to divide both sides by 10. 1 divided by 10 is 0.1. Okay, now I'm going to natural log both sides, so I'm going to get that right there, and then divide by this long decimal right here. We have our graphing calculators that can take care of that, no problem. And I get 80,923 years. Okay, now typically, you guys, when you have big numbers like this, they typically round it to 3 significant digits, and I'm surprised I didn't do that in this lesson. So you might see an answer like 80,900 years. Okay, that would be 3 significant digits. So just depends on you know, what kind of answers you're looking for. Okay, so here's another example. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern, so that's my formula, that tells me to use my formula, y equals c e to the kt power. Exponential pattern of decline, what will they be after another 2 months? Okay. So, so after another 2 months, check it out. We started with 4 months up here. After another 2 months, so I'm going to somewhere use 6 months in there. T equals 6. But for now, you guys, y equals c e to the kt power. Okay, so the final is 80,000. We started with 100,000. I don't know k yet. And again, I'm going to do it after 6 months, you guys, but what I have to do is figure out K first so I can get my K right there. So after 4 months, I have this information right here. So let's go ahead and plug that in and get K. Okay, so divide both sides by 100,000, you get 0.8 equals E to the 4t power, and then natural log both sides. Okay, and then I'm going to divide by 4 right here, and the natural log of 0.8. Divided by 4 gets me a negative 0.0558. Okay, so that's going to go in right there, which is going to go in right here. Okay, and then I'm going to do, so after another 2 more months, t is going to be 6, you guys. Okay, so we're looking for the final amount. What will they have after another 2 months? So that's my new final amount, which is y. I'm looking for y. My initial amount is going to be 100,000, and my time is going to be 6, so you plug that into the calculator right there. All right, now this one I went ahead and rounded to 3 significant digits right here, so 3 significant digits is going to make that 71,500 units. Okay, all right, and that's it, you guys. If you're in my calculus class, I would assign something like that for your homework. Take care, you guys.